Swayam Prabha. Digital India. Educated India.
Okay. Looks a little neat. So I have this, this, right? So viscous terms, are negligible except near the walls. So if you have a free shed jet, viscous terms are negligible. Okay. All right. So I think that's all. So this is essentially the equations, like I said, the boundary layer equations, which we have, in which we have incorporated turbulent definitions of the velocity, and this is how it looks like. Okay. So really that. Okay. So in the next class, well, I'll do a couple of maybe some mathematics a little bit, some couple of examples. We'll do that. And then we're going to move on to something very interesting. What we're going to talk about, that what kind of, how does the turbulence change when I start looking at different length scales. If I'm looking at the flow from a bigger length scale compared to if I'm looking at the flow from a smaller length scale, then do they differ? And it's not just like they look different to me, it's not like that, but in the sense that are the flows themselves physically different? If I look at a bigger, or is it that the fluctuations are larger just because I have a bigger length scale, or is it more than that? Do the physical properties themselves change, right, from if I change the length scale? So I'm going to talk about that. That's the next one. Before that, I will probably do a couple of examples, sort of to take stock of what we've learned so far.
So we've spoken about free turbulence. So we've spoken about actually a free turbulent jet, right? And in that we've spoken about how the jet is self-similar, and this self-similarity is something that is basically from the concept which is introduced for boundary layers, right? So free turbulent flows are essentially bounded on at least one side by ambient fluid of nearly same density, which is not turbulent and is irrotational. So what you see here are these two sections that drawn kind of velocity profile. Now self-similarity essentially means that the velocity profile at section 2 is just a scaled up version of the one that you see at 1. Or in other words, they're essentially the same flows at 1 and 2, except by they differ by a certain factor. Right? So that's what we understand by self-similar. The mean value equations are simplified using boundary layer approximation. This is the boundary layer approximation. And such a free turbulent jet is therefore considered to be self-similar. And is it possible that a flow which is developing in such a fashion may not be self-similar? Yes, examples are possible. But we'll talk about something else here. So this is a self-similarity that we have essentially spoken about for so long. And what we'll talk about, another aspect of something like this is something we'll talk about is self-preservation. Okay, and we'll talk about that in a little more detail. Okay, So now self-preserving, right? If a flow has to be self-preserving, right? So I'm going to write this down in mathematical sense, right? Now, M basically represents the mean value quantity, okay? Mean value quantity. And it should take this form, okay? So M is equal to M1 plus M naught, function of Y by M naught and Z by M naught, okay? It should basically, the mean value of the quantity, which is represented by M, should take on this form, okay? So let me write down what these things mean. So L naught is a scale of length, M naught is a scale of the quantity. M1 is the reference level of the quantity in free stream. For example, if it's velocity, you could write that as V infinity. So, right, so I could write that as M infinity, for example. So it's a reference level of the quantity in free stream. And all of these are functions of x alone. So this concept of self-preservation embodies the principle of moving equilibrium. So it basically means that the conditions at the initiation of the flow, when the flow begins, right, is largely irrelevant in the sense that the conditions at which the flow began, do not matter, okay, at instances of time which is much later on. Okay, so when I'm looking at a particular flow at some instant of time, right, it does not, the conditions at which it had been initiated, which is some time back, do not matter. Okay, flow depends on one or two simple parameters and is geometrically similar at all sections. Okay, so essentially I do not, in the sense that when I look at self-similarity here, so what is happening at location 2 is exactly the same as what it is happening at 1, except it is just there's a scale between 1 and 2. It's at a different scale. That's a different factor. So if you take the velocity at 2 is just and divide and the velocity at 1, they're related by some factor. Self-preserving, you cannot do that because they are there is no relationship. So it's no relationship. Having said that, the flow is in equilibrium at every location, at every instant of time. So therefore, the concept of moving equilibrium. It is in equilibrium, but it doesn't depend on the conditions at which it started. So almost like, so let me, I think what I'm going to write down now is the self-preservation conditions. We need to introduce these mathematically into the momentum and energy equation by using self-preserving distributions. This is how I've just written down this form M. So now for that I'm going to use, say, the velocity, the x component of velocity. So I write that down as so U now looks like something like this, right? U1 is essentially U infinity, and small u is the scale of the quantity itself, the velocity itself, and which is a function of z by L naught. Okay. So let me write down these various distributions. Okay. So in a normal sense, while we use the u infinity or u, right, here we have a distribution. This distribution is, if the flow has to be self-preserving, then it needs to follow such a distribution. That's the point. So which is what I'm writing it out. So writing out several of these quantities according to this distribution. So I'm assuming that these are all self-preserving. Now we'll find out whether that holds true. Okay, so we write down this distribution, introduce it into the momentum and energy equations, and then see what are the conditions which will make these self-preserving. So essentially u1 is nothing but u infinity, is the free stream velocity. So u naught is the scale of the mean velocity variation. Q naught is the scale of turbulent velocities. L naught is the length scale of the flow. And all of the above are functions of x alone, and they're independent of position and characteristic of the whole flow. Okay. So now I think our work is cut out. So we have written down a self-preserving flow, right? How does this? What does that mean? Okay. So this is our. Let's write down the momentum equation as we know it. Dx, right? So now essentially we are going to introduce, the distributions, which is self-preserving distributions. So basically replace u and the other quantities with what we just wrote out, right? So introduce the self-preserving nature of the flow into the momentum equation. This is the distribution we wrote out. That's for the self-preserving distribution, right? So we use that into we introduce that into the momentum equation, and let's see what we get. So now, what sort of equation we get? So the momentum equation, as you can see, with the self-preserving distribution now, looks pretty, pretty daunting, right? So we have this large sort of equation that we set up. Okay. So now, how do we go about, sort of understanding what is going on here? Now, eta is essentially z by L naught. Okay. And so essentially and the dashes signify differentiation with respect to eta. And unless the u infinity, right, or u1 here, it changes by a large factor in L, the transverse velocities are smaller than the longitudinal velocities by at least a factor, small l by n, right? So we are essentially saying that. So now, so that's that. Okay, so we have this large equation now, and the point is, how do we go about understanding this? What do we do, right? So this particular equation that we see here, right, the several terms on the left hand side is equal to 0. So the idea is, what are the conditions under which this equation will hold? So for this equation to hold, right, coefficients of each term has to go to 0 for this for this equation to hold, or they are proportional to each other, right? Makes sense? This entire equation needs to go to 0. How will that happen? We've got several terms, first term plus the second term, so on and so forth. Now this term, q naught square by L naught G13 dash, okay, this is essentially the Reynolds stress term, right? And why am I sort of pointing that out, right? Because in turbulent flow, Reynolds stresses and velocity gradients, right, they are definitely not 0, right? So in this equation here, right, in this equation here, this particular term is a Reynolds stress term, right? But that is definitely not 0. That term is definitely not 0, right? So what we can do is divide the entire equation by the coefficient of that, right? So q naught square by L naught. We divide the entire equation by that. So, please go ahead and do that and see how each equation, each term turns out to be. I'm just writing out a couple, okay? So the first one, for example, so I'm dividing that, this small b naught there, L naught by q naught square, du1 dux. So, for example, the first term, right, that's how the coefficient looks. The second term is u1 into L naught by q naught square into du naught dx, right? These are essentially the coefficients of f, right? So we need to look at all the coefficients. So all the coefficients will change, right? Okay. Now, all these coefficients would either be 0 or independent of x, right? Now this q naught by u naught is essentially energy dissipation, right? And that's about equal to 1, right? That is, q naught is equal to u naught, just about equal to u naught, okay? Okay. Now, so we will basically then look at the specific cases. So for the case where U naught is essentially, U1, which is constant, in that case dl naught dx is equal to constant. This, such a flow, in such a case, right, a mixing layer between two uniform flows, okay? So this, this is a condition for the mixing layer between two uniform velocities. Two uniform flows of different velocities. If they are self-preserving, should satisfy this condition. So that this condition, if it satisfies, then it will also satisfy self-preservation. On the other hand, if U naught is proportional to U1, which is essentially proportional to distance x, and dl naught dx is constant, this self-preservation is applicable for wakes and jets. With suitable external pressure gradients. Defined by 1. Okay, so these are essentially the this is how we can sort of self-preservation on like specific flows, right? So mixing layer between two uniform flows and wakes and jets say. Okay, so these are two different kinds of flows. Now, if they have to be, if they have to exhibit self-preservation capabilities, then how does that translate mathematically? What does it mean in terms of velocity or other properties? So this is what it means, okay, as we've written down here in terms of the equations. Okay. Now, the self-preservation can also, something can be like, it can be sort of not very distinct, but it can be approximately self-preserving. So that's when U naught by U1 kind of varies slowly. Okay. So there can be flows that do not satisfy these conditions for self-preservation exactly, right? So this U naught by U1, as I said, it varies slowly. So it is it's kind of they follow, but not very distinctly. Okay. Now, the Reynolds stress, right? Reynolds stress, it takes time to develop and decay. Existing rates of spread, right, of the conditions upstream. So hence, of the mean velocity distribution does not of the stresses, quality of rates of. Okay, this is a little bit pointers to realistic thing. Okay, the distribution we have taken here. So we need when we equations and we are which they have to be satisfied. There might be flows which, like I said, they do not these conditions, right? But they do exhibit some self-preservation quantity, some preservation characteristics, right? And which may not be very distinct or very pronounced, but still, likely. So one of the reasons, for example, the Reynolds stress, it doesn't develop suddenly, right? It does take time to develop, and it takes time to decay, right? And at a particular location, although we've said, this is moving equilibrium and everything, but the Reynolds stress, the existing at that particular location and time, how much it is spreading, at what rate, is dependent on what was happening earlier for conditions upstream, right? So, although there is symmetry of the mean velocity distribution locally, it doesn't mean that it was always the same, in terms of history of how the flow has been developing since it sort of started out. So those are kind of a few pointers to this whole discussion. Now, non-existence of symmetry may be a natural outcome of the flow. So although there is local equilibrium, right, self-preservation possible, right? So there is local equilibrium, self-preservation is possible, but it may not be axisymmetric, right? So what we're trying to say is that the flow itself, in order to be in equilibrium, actually becomes axisymmetric. Non-axisymmetric, and does not enforce the axisymmetry.
Okay, so I'll stop here and sort of take that up in the next class. Thank you.